So we're going to illustrate using a tree diagram to come up with some probability numbers. So our scenario: to treat a certain illness, doctors use drug A 80% of the time, drug B 15% of the time, and drug C 5% of the time. The failure rates, which is the chance that the drug does not work, are 40%, 60%, and 80% respectively for the drugs. So what we're going to do is come up with a tree diagram here. First, we would have to know what drug was chosen. So either drug A is going to be chosen, drug B, or drug C. And we know that 80% of the time, or probability of 0.8, drug A will be used. 15% of the time, or 0.15 as a probability, drug B will be used. And 0.05, 5% of the time, drug C will be used. Okay. Now, regardless of which one of these drugs are used, there's two things that can happen for each drug. It can either work or it cannot work. So we're given the failure. I'm going to let the top tree or the top branch of each one of these represent that it works. So this works, and this works. And these are does not work, and does not work. So there's a 40% chance that this does not work, drug A. So that means that there's a 60% chance, the complement of 0.4, that it does work. If it's 40% chance that it does not, 60% chance that it does. Okay. There's a 60% chance that drug B does not work. That means there's a 40% chance that it does. And there's an 80% chance that drug C does not work. That means there's a 20% chance, or 0.2, that it does work. Okay. So basically there's only 6 things that can happen in this scenario that we're talking about. We can use drug A and work and have it work, drug A and it not work, drug B and it work, drug B and it not work, or we can use drug C and it work, drug C and it not work. So we're going to come up with these 6 probabilities. So the first equal sign here represents using drug A and it working. So that's 0.8 times 0.6 because they're both happening. And that is 0.48. This is using drug A and it not working. That's 0.32. Now notice that these two add up to be 0.8, which is what the combined probability of drug A is. And these 6 probabilities have to add up to 100%. That's the only 6 events that can occur. So using drug B and it working, that is 0.15 times 0.4 is 0.06. Using drug B and it not working, 0.09. Notice these add up to 0.15. So these 4 probabilities add up to 0.95. They got the 0.8 plus the 0.15. So drug C and working is 0.01. And then drug C and not working is 0.04. That gives us the last 5%, which these add up to 100%. Okay. So now we're going to use these to answer a couple questions. So the first question says, what is the probability that we use drug A and it works? That's in probability notation there, but that's what that means. Drug A and it works. And that is right here. Drug A and works is 0.48. That's 48%. That one's pretty easy. Now the next one says, what is the probability of A or B? What's the probability that you use drug A or B? Well, these are mutually exclusive events, or sometimes we call disjoint events. You're not going to use joint drug A and drug B on the same case. Well, I guess that is possible, but it's not relevant to the problem here. So they're disjoint. So you can just add those up. That's 0.8 plus the 0.15. That's a 95% chance that either A or B is used. There's a 5% chance that you don't use B, or A or B. Okay. The next question says, what is the probability that it works? So we have 3 events that indicate that it works. That is drug A and it works, which is 0.48. Drug B and it works, which is 0.06. Or drug C and it works, which is 0.01. If we add those together, we get 0.55. So that's the probability that it works. Or that a drug works. Okay? Now this says, what is the probability of that it's A or works? Okay, so we already have, so let's just go through each one of these individually. If it's either A, using drug A, or it works, it's going to satisfy this condition. So this is satisfied for 2 conditions. This one is also satisfied because it's drug A. This is works, so it's satisfied. This one is not satisfied because it's drug B and it does not work. It doesn't satisfy either one of these. This is drug C and works, so that is satisfied because it works. This one is not. So if we add up these probabilities, we have 0.48 plus 0.32, that's 0.8, plus 0.06 is 0.86, plus 0.01 is 0.87. We have an 87% chance. Now we either use drug A or the drug works. Some drug works. Okay, so we also could think about this as a probability formula. The probability of A or works. And we should remember that that's the probability of A plus the probability of works minus the probability of A and works. Now take away that joint probability. So let's think about this. What's the probability of using drug A? That's 80%. There's an 80% chance that we use drug A. Plus the probability that it works, and that's any drug works. That's 0.55. That's one we just used, or we just come up with. That's adding the 3 works events together. And then we take away the probability of using A and it working, which is 0.48. We take away 0.48. And you can verify that that is 1.35 minus 0.48 is our 0.87. Okay. Next question says, what is the probability of drug A given that it works? So to make this make a little more sense as far as a problem, given that a drug has worked, what is the probability that it was drug A? Okay. So first let's think about our, what I like to call our universe is works. I'll go ahead and do my universe is what I'm dividing. I'm already given that is working. So I'm dividing it out of a probability of 55%, because it's 55% of the time it works. Now of that 55% of the time, 48% of that came from drug A. Think about how we got that 55%. It was the 48, the 6, and the 1%. So the 48% out of the 55% is what our joint probability is going to be. So whatever that answer is in the calculator, I'm not going to do it in the calculator because we can do that, but that's what your answer would be. Okay. And I'll also show this. The probability of A and works These are all probability formulas. I'm just kind of showing you a couple of different ways. That is the probability of A and W divided by the probability of W. And that's exactly what this formula says. The probability of W, the probability of working, is 0.55. The probability that we use drug A and it works was 0.48. So that's the same answer. That's just verifying that formula there. And the last problem we're going to do says, are the events drug A and works independent events? So if two events are independent, then what you will see is the probability of A, if these two events were independent, then the probability of A would be the same thing as the probability of A given that it works. Or you could do it the other way. The probability of it working would have to be the same thing as the probability of it working given that it came from drug A. Okay, so I'll put both of these down. You can check either one. They really both have to be equal to be independent. Okay. So I'll just use this one. It doesn't matter which one you do really, but the probability of working, we already know, is 0.55. We've got that a couple of times. That's the 0.48 plus the 0.06 plus the 0.01. Now we're going to try to see, is that the same thing? Put a question mark there. Is the probability that it works given that you're in that you use drug A? Well, let's think about it. Given that we use drug A, this is my universe now. This is my universe. So given that I'm in universe A, what's the probability that it works? And that was 0.6. 0.6. So that's my conditional probability here. So the fact that they are not equal means that the events are not independent. Now I will state here that you can see that these probabilities are fairly close. So they might not be independent, but there might not be a very strong correlation either, since they are pretty close. If there's a strong relationship between those two events, then you will see a bigger discrepancy between the probabilities.